Thank you for organizing this nice meeting and for having me here. And in this talk, I'm going to discuss two concepts, the excitonic insulator and cavities, which are at the basics of this workshop. And I'm going to discuss how these two concepts are related to various types of polarization that can be observed in matter or cannot be observed, actually. And actually, part of this talk will be about open questions on how about how these three concepts are related to each other. So this research activity goes in the main direction of trying to find a way to control quantum materials with light. And so this is something that it's very interesting, because in quantum materials you can have a wealth of different types of collective phenomena which arise from strong correlation between the microscopic degrees of freedom. And this strong correlation makes the fact that these materials can have very strong response to external perturbation. And in a very promising line of research is to find a way to tune these collective phenomena in a switchable way. And light has become one of the main tools for exploring the frontier of the control of quantum materials. So we have heard before the talk by Andrea on how to use strong laser source to control these materials. And in this talk, I want to follow the way of using light in cavities. So now let me say why I want to use cavities to control quantum materials properties. So the main reason why I think that, my personal opinion, cavities are interesting for controlling properties of quantum materials are for two main effects that can be obtained by coupled matters in cavity. So here there is a sketch of a cavity in which you have light resonating between two mirrors, and some matter, some materials, can be a material or something else in between. Now, while the light is resonating, it's continuously interacting and exchanging energy with this material, so that the new excitation of the systems becomes entangled excitations and are called generically polaritons. Now, here is an example in which there is an exciton mode in blue, which is coupled to a cavity mode in red, and then you have the formation of these two new polaritons. Now, what does it mean forming polaritons? Well, the first main effect of a polariton formation is the fact that one can tune the energy of some matter excitation. In this case, you can open a Rabi splitting here, and then have two polaritons, and so basically tune the energy of your exciton mode in this case. So now, this can be very important for collective phenomena that can involve some softening or some matter excitation which control the emergence of some collective phenomena, for example, phonon in superconductivity. The other interesting thing of the formation of polaritons is that a polariton is entangled with the light mode, is entangling a collective number of a large number of microscopic degrees of freedom, which means that actually this polariton formation will mediate effective interactions in the materials. And these effective interactions in the material can actually compete or cooperate with the interaction which are intrinsic to the quantum materials to bring about new collective phenomena which will involve light and matter. And recently there has been various proposals for using these two kinds of effects to control, for example, superconductivity. In this talk, I'm mainly focused on a collective phase of matter which actually involves excitons, which is the so-called excitonic insulator. Now, excitonic insulator is a phase of matter that has been introduced 50 years ago or so. And basically, an exciton, you have a semiconductor with two bands. You can excite an electron from the valence band to the conduction band. Now, due to the Coulomb attraction between these two negatively and positively charged particles, these two can form a bound state, which is called exciton. Now, excitonic insulators are systems which are unstable toward the creation of excitons. And so they realize a ground state, which is characterized by a macroscopic number of excitons, basically, which is an exciton condensate. So now this kind of phase transition has been discussed in this simple setup of two-band systems. But I would like to mention the fact that the concept of excitonic condensation is actually broader than the concept of excitonic insulator itself. Indeed, the excitonic condensation can appear also in different kind of system. For example, in bilayers in which there are indirect excitons. So a typical framework is that one has two layers of different materials, and one can apply a positive gate on one side and a negative gate on one side on the other side in order to create positive electrons on one layer and holes on the other, and let these two species to interact electrostatically. And then below a critical temperature, there can be a condensation of this object. Now, this is different from what I've described before, because in this case, one uses a gate potential to create an exciton and then cool down the system to condense. In what I've shown before, in this phase transition, is the spontaneous generation of exciton and the spontaneous condensation of this object. And here I just put a non-exhaustive list of very interesting works going on looking for the excitonic condensation in this kind of bilayer system.
These are experimental.
These are experiments. No, all of these are experiments.
So why do you differentiate it? I mean, gate voltage is just for alignment, right? So it seems to me like it's conceptually, it's really not that different from.
Well, in this case, they're not aligned. You have a band gap between the two, so you are not bringing this band down.
But
here.
you can also imagine in a bilayer system that you can actually change the energy levels and see how excitonic insulator state would survive.
Yeah, you
so
can do
it
this.
seems to me like it's a tuning knob rather than sort of a different.
Well, yeah, it's a tuning knob, but here you're creating actually you're making a population of holes on one layer and a population of electrons in the other. In a bulk system, in a semiconductor, in order to create an hole and an electron, you have to provide some energy. Here, the energy is provided by the gate potential. But yeah, it's a tuning knob to have, let's say, a finite population of excitons. Okay.
Sorry, may I ask you a quick question?
Yeah, sure.
So hasn't it been observed at some level in quantum Hall systems by Giacomo Mazza?
Yeah, that's indeed this is one of these paper here. Yeah, in the case of bilayer graphene, actually. In the case of graphene. Yeah.
No, but there was previous. This is not important, but it was previous in like 2000 or something. Jim
Jim
Eisenstein and
Eisenstein.
bilayer quantum.
Okay, yes,
it
probably,
was
yeah.
1/2 quantum Hall systems.
Yeah, I think that was this paper.
That was
here
probably
also,
what
yeah.
was
It's before it.
Yeah. Doesn't matter.
Yeah,
It
okay.
was observed.
Yeah, maybe I missed some reference here, but that's just. Okay, now, so these are for this artificial system in which you have this indirect exciton, namely living on two different layers. Now, what about materials? So, in real material, what actually happens usually is that this excitonic transition is usually coupled to other kind of instability of the systems. So these are two of the most famous candidates for hosting this excitonic insulator phase. This one is the titanium selenide that has this excitonic phase, which is coupled to some charge ordering. So you have a charge ordering of the system also. Well, this is the material that, as Antoine has mentioned before, will be the main topic of the tomorrow talks. And I didn't put any reference here because I didn't want to. I just put the reference of the picture of the paper from which I took this nice.
So sorry, Giacomo, this tantalum nickel,
Yeah.
is this a new material? Have people known it for decades?
Well, it has been known from.
For decades.
But not in this
decades.
context. People have recently
Yes.
realized that.
It's easy to actually.
Yeah, well, let's say that I think that the first proposal for this material for being excitonic insulator dates back to the end of the 90s, if I'm not wrong. that was the first, one of the first, yeah, but let's say in the last decade there will be a strong interest of trying to find a way to probe the excitonic insulator phase of this system. So now I'm not going to detail because tomorrow we will have a full bunch of talk covering this topic. I want just to say that in this case, the excitonic transition is likely to be coupled to the breaking of the discrete symmetry of the lattice, so to structural transitions actually. And I want just to advertise the talk by Mark Rosner tomorrow that will address this point. Okay, so so now if we focus just on the pure excitonic transition, how an excitonic insulator is formed. So an exciton is a resonance in the spectrum of absorption of your material. And here there is this spectrum in a case of a just system with two bands. And this spectrum is here, and in order to create this exciton, one has to provide an energy, which is this Ex, which is basically the difference between the energy of the gap, namely which is the energy that one needs to create a particular excitation, minus the energy which is gained in forming the bounded pair, which is the binding energy. So here you have the energy of the gap, this is the binding energy, and this is the energy of your excitonic mode. So now what happens when once you put you tune the parameter of your system? For example, here in this phase diagram, I'm tuning temperature and interaction between the two bands. What's happening is that, for example, if you start here from this side and you lower the interaction and you go towards this green area, which is the area in which you have this excitonic insulator phase, what's happening is that this excitonic mode is becoming soft, so it's going down. So basically, this means that the energy gained in forming the bounded pair is larger than the energy required to create the pair. So this means that the system will be unstable toward the creation of this pair and form the condensate. So this is just moving in this direction from the excitonic from in this phase diagram, whereas this is moving in temperature now. Now I'm starting from high temperature, I'm going down with temperature, and then there is this mode that is becoming soft. So this is a soft mode transition. So the idea then is to use a polariton, so hybridize a photon field with this excitonic mode in order to stimulate the softening of this mode and actually control the emergence of this ordered phase.
Sorry to keep interrupting you. So this phase diagram, where does it actually come from?
Yeah, so this is just the two bands like this. Two bands like this plus an interaction between the two bands and this mean field theory. Basically, it's BCS.
But that's Keldish 19.
Yeah, that's the original.
That's actually from his paper. That looks like a newer benefit.
No, it's not from this paper, but let's say that.
It is a recoding of the content of his paper.
Okay.
Oh, it's Cohn, Jerome.
Yeah, it's let's say the first
New incarnation. Okay.
So now in the lower left corner is this same insulation statement.
the lower left. Yeah, no, okay. So now on this blue side, actually the high temperature, let's say it's semiconducting on the blue side, whereas on the red side, what's happening is that the two bands overlap, so you have a metal. So yeah, and this is separating also the regime in which the exciton condense actually. On this side, it's really a mode that is becoming soft, like the one that I've shown here. On this other side is an instability more similar to BCS superconductivity, basically. It's an instability of the Derby surface.
Sorry.
Yeah.
But this is a Hubbard-like model. This is short-range interactions.
Yeah, this is a Hubbard-like.
Fine. So that's why it doesn't have kind of first-order stuff further out.
The first order on this side.
Yeah.
Yeah, it's really it's rather steep, but it's not first order. In this case, it's second order. Okay, so this was the general idea, and this is what we try to explore in this paper, in which now we take this model with this Hubbard-like interaction, and we couple to a single mode cavity field. And here you see that we are starting from, let's say, above the critical temperature, away from the phase that I've shown you before. And then by coupling with increasing the strength of the light matter coupling, you can see that this exciton mode becomes softer, and that at some point it becomes zero, signaling that at this point there is this excitonic condensation which is taking place. And what is the result of this is basically that by changing the strength of the light matter coupling, one can change the boundaries of your phase diagram. And here, this is the original phase diagram that I was showing before. And as you crank up the coupling strength G, then you have that just the boundary moves. So basically you are enhancing the phase space for this excitonic insulator phase.
I'm sorry, Jeff,
Yes.
you go back one slide. So at zero coupling, what are go back one more. At zero coupling, what are the modes? What are the two modes there?
Okay, so yeah, sure.
Yeah.
Thanks for the observation. Yeah. So actually here I'm observing the exciton polyton looking at the photon properties. So here basically at zero coupling there is no exciton polyton, there is just the photon mode here. Then as
under the red arrow, it's just black. There's no
It's black.
Exactly,
I see.
exactly,
So
yeah.
only for finite coupling does this low energy mode appear.
Exactly.
I see.
So let's say if you want, it's a way of observing this mode. So this mode, of course, is already here, but in order to observe, you have to do some transmission experiment and look, for example, the transmission of the cavity, which is basically measuring the spectral density of your photon field. Yeah.
And sort of generally, I mean, this is a highly naive question, but generally, as I walk the light matter coupling, does the oscillator strength, is the oscillator strength just being transferred, or does you just pick up?
What do you mean, just pick up? Yeah.
Is there a new oscillator strength that the cavity adds?
What he wants to know is if you fix the light matter coupling
Yeah.
and you take the absorption spectrum and you integrate it over omega, you get some answer, which is a spectral weight.
Yeah.
Okay.
He wants to know how that answer depends on the strength of the light matter
Okay.
coupling, right?
Does the light matter coupling
okay,
shift
they-
the spectral weight around, or does it create new spectral weight that I didn't have before, generally, when I put something between two mirrors?
I think in this case, it's just keeping the spectral weight is constant in this case. It's
The
just
total spectral
the
weight.
total spectral weight is constant.
No, it always keeps
I
the
would
whole,
say that
it only shifts around.
integrated.
It only shifts
Some
around.
shifts around.
This is a general
Yeah.
statement about nature. I mean, regardless of how strong the coupling is made.
Yes.
I see.
Sorry, another question just to make
Yeah.
sure I understand it. So you have a dipole matrix element between the two bands?
Yes, yeah, of course.
Fine.
If
That's
you
okay.
have-
So that
yeah.
you say, so in some sense, there's a hidden assumption here that bottom band is S, top band is P, or something.
Yeah, exactly. Sorry, I didn't mention this before. Yeah,
So
that's-
there's-
yeah, of course. If there was
Which
no,
is, I think, really the answer.
if there were no dipole matrix element, then you would not able to observe any exciton polyton, basically. Yeah. Okay. Okay, so now this is an enlarged phase diagram that you can obtain in this case, but now you have seen that whereas in the green case you have just an exciton mode that becomes soft, here you have an exciton polyton mode that becomes soft, which means that when you are in this yellow phase now you have both the excitonic order parameter, which is this object here, basically the hybridization between the two bands, and the amplitude of your photon field that becomes non-zero. So basically you have a simultaneous instability of the light and matter. And this you can just understand this but just by writing down a simple Landau expansion for your free energy, in which you have the phi is the excitonic order parameter, so you have a fourth theory, Landau theory for your excitonic order parameter with some critical temperature. Then you have just a quadratic free energy for the photon field, which is not critical by itself. And then you have a linear coupling between the two. And as just coming back to your question, this linear coupling basically is just is roughly the intensity of the light map of the field inside the cavity times the local value of the dipole matrix element in your system. So if this term is zero, is non-zero, sorry. If this term is non-zero, it means that every time that phi is different from zero, a small coupling to the photon field will basically drive a combined instability of the light matter, which actually will enhance the critical temperature of the system. So for some historical reasons, this state in which you have a coherent state of light is called superradiance. And in this way, we call this state superradiant excitonic insulator. Now, let me just say that this is a very misleading terminology. The name is superradiance, because indeed this is a ground state phase transition, so nothing radiates in the ground state. And this term has been introduced in the 70s in these two papers that were looking at the Hamiltonian, which is a very simplified version of the light-matter interaction, which you have only spins. And this model, if you just solve this model, you can solve really easily as a phase transition indeed. Below a certain critical temperature, you have no expectation value of the photon field and no ordering of the spins. Above, you have a macroscopic expectation value for the photon field and some ordering of the field. Now, so I say that this, if you just take this model and this is the ground state of your model, there is no radiation around. So if you want to see some radiation, you have to do something, your system, you have to perturb it. And this is an example of, you can play this game of starting with your condensed phase and opening a bit the coupling with some external bath, and then you see that there is the emission of some light pulse, which depends on how fast you do this. If you do a quench, you have a strong light pulse which is emitted. If you do adiabatically, you have a very weak light pulse which is emitted. If you do this slow enough, nothing will be emitted for your system.
Sorry, Giacomo,
Yeah.
but the reason why that light is emitted is that by moving the mirror, you're doing work on the cavity. So the energy comes from my finger.
Exactly.
It was not in the, right, okay.
Yeah. If you do this very, very slowly, in the adiabatic limit, nothing will appear outside because you have...
No, but the point is that, but by definition, if I move the mirror, I'm putting energy into the cavity.
Exactly.
I just,
Yeah.
No, but that means that if that means, what you're saying is that if I did something else that wasn't moving the mirror, but I just wave my fingers and change the mirror from completely reflecting to completely transparent, would something come out?
But you still need to do work. You need to have a node of the electromagnetic field somewhere.
Well, but I don't have to do very much to make the mirror go from reflecting to transparent. You know, if I think about these switchable mirrors. Anyway, but that's the question is, would I get something what would come out if I just changed the mirror from reflecting to transparent?
Well, you will kill this phase and you will have the photons that are the virtual photon that were trapped in the original phase.
Okay, but that comes back to the meaning of expectation value of A operator.
Yeah, I'm coming back to this. Yeah.
I mean, sorry, but you do have, some static electric field because you've got a bunch of aligned sort of macroscopic.
I'm coming back to this
so you're
question
going
in a minute.
It's a ferrite.
This is
Or a ferromagnet.
Okay, yes. I think that this question will be.
But I think this is an important question. I think is if you don't do work, and if you were going to remove for whatever reason the mirrors, you don't get photons.
If you do this in this case adiabatically and you do any work, you don't get anything outside. That's what I would say. If you do a quench, so if you do some work, okay, so this is what just to say that this is just a game playing with this state put inside the cavity and then let the thing open. Now, if I come back to this, if you come back to this phase transition, of course this has been introduced in the 70s, but from the 70s to nowadays actually, there has been a bunch of several different types of Novo theorems actually stating that this phase of matter cannot appear at all. So here I don't don't want to enter into this debate about this no-go theorem. This no-go theorem are basically related to the commutation relation between momentum and position and to the diamagnetic coupling. Here, what I want just to say is that if one looks closely at this ordered phase of matter, one realizes that the ordering in matter that is created by this super-Radian phase transition is an excitonic insulator. So if this phase transition cannot exist, then cannot exist the excitonic insulator, I would say. Well, of course,
I understand that it follows that it's an excitonic phase because it has a non-zero expectation value of sigma x. Why does it follow that it's an insulator?
Oh, okay. This is another historical jargon that might be.
So the super radiant excitonic insulator neither super radiates nor is it an insulator, basically.
Well, yeah, you know, okay, I'm not spoiling anything, but okay. So now, what does it mean? So what does it mean having this phase of matter? So that is the question, because the excitonic insulator is a phase that realizes this guy here. So basically, any infinitesimal coupling will drive this and basically goes against this transition. So in order to understand this, I'm considering a single dipole now. So you have a single dipole, for example, an harmonic oscillator. And this H0 is the Hamiltonian of your harmonic oscillator. And then you perturb your Hamiltonian with some hybridization between the two levels. So I want to simulate what does it mean having an hybridization between two levels. Well, and this is crucially depends on the phase that you pick up on this lambda. If lambda is real, what you have is that the density is shifted with respect to the zero. Basically, you have a x expectation value different from zero. Whereas if you take lambda, which is imaginary, what you get is that you have a current density now here. And I don't know if it's clear, but these two are not symmetric, these two lobes. And if you integrate this over space, you get a finite value of p. So now, in real life, if you want to, this lambda would correspond to some external fields that will enter in your Hamiltonian. Here are just parameters that I put just to see that in one case, yeah. So, but in an excitonic insulator, what's happening actually is that this hybridization is happening spontaneously, without any lambda. There are interactions that are creating this excitation. And actually, then one goes back to the problem is that the phase of the excitonic insulator determines the macroscopic property of the system. And in particular, if you write the condensate of the parameter like a modulus times some phase factor, when phi is 0, so this is a completely real, purely real order parameter, modulus the fact that quantities like polarization are not so well defined in an extended system, then in this case you get something which is a charge density wave or something close to a ferroelectric. Now, if you go to this other state, you go into this very disturbing phase of matter, which is a ferrocurrent, basically. Basically, it's a state in which you have basically P different from 0, and so there is an homogeneous current flowing through a system.
So this is in what way is that a current?
Well, in what way is that the P, the expectation value of the current density is of the
But
integral
these
current
are like
density.
vortices that you have in the system. So the total, it's not the current goes from left to right. Or
No, this is the integration, the integral of all the current density. It's like here. In this case, it's the integral of the current density.
Somebody should think that it's a current circulating amongst the two orbitals, but there will be some kind of topological thing, just like in the case of
Exactly.
ferroelectric
Yeah.
ventricles that will lead to edge bursts of some
Yeah.
kind.
Yeah.
That's the way to see it.
That's the way to see, but it's not really. Yeah, I'm going back to this.
But
This is not
what
a
about the
real-
second principle? What about the
And it's not
principles
a
of
real
thermodynamics?
current.
Yeah, well, okay, this is very disturbing. I would say that it's.
You have nothing against ferroelectrics.
No.
Yeah, exactly. You don't have a ferroelectric either because
You have nothing
I
against
don't have
ferro-
anything against ferroelectrics.
So why should you have anything against this? It's not.
Yeah.
I don't think it's fundamentally different.
But this is a current that doesn't. This I mean, does it? Where
Oh no,
does
this
it
is,
need
this is
energy?
an orbital. This is an orbital ferromagnet.
Yeah, it's
well, okay. So well, let me come back. Let me come back to this.
I'm sorry.
Okay.
Yeah.
Yeah. So these two phases now are completely degenerate in this excitonic insulator. And now when you couple with field, what happens is that you are lowering the energy of this phase. So you're lowering, you are entering this disturbing phase, basically you're lowering the energy of this ferrocurrent state. And actually this ferrocurrent state is something that has been discussed in the early days of excitonic insulators, actually, in this paper here and in another series of papers on this design. And of course, yeah, here you have a state in which you have an homogeneous current. And how one can think of this state? Well, first of all, this state can exist only if you have an infinite or periodic systems, actually, because otherwise you will just move charge from one side to the other of your system. And in general, the way of thinking of this state is that, as in the ferroelectric, the two orders will somehow hybridize and breaks down into various domain walls. So as in a ferroelectric that breaks down in domain walls, in this case you will have some different kind of domain walls in which you have the, like in this figure here, which I took from this paper here, I guess.
It's not really a current, no? What you get is a polarization.
Well,
it's the same argument of the theory of polarization in solids. You can see it as a current going through the boundaries or something, an accumulation of charge at the boundaries. And this is what David Vanderbilt just called a macroscopic theory of polarization, and the polarization is a not well-defined modulo pi.
I think that what you're saying is that basically when you have ferroelectric, you can measure only the changes, changes in the polarization.
There is no way to access that current.
Yeah, and the changes in polarization, you measure it by looking at the current that you generate by displacing, for example.
And it's the same here, I guess.
Well, here is you should find an analogous to the state. Okay. But just to say that here, if you look as a function of space, one is moving the phase of your excitonic condensate, and the one goes from, let's say, 0 here, you have a ferroelectric, then you go to pi half here, which has a ferrocurrent, and then you go to pi, and so. And basically, what does it produce? It produces some circulating current, some current pattern inside your system. And this has been discussed very recently, also in relation to this paper, in the case of spin current in excitonic magnet. And also in this case, if you apply some mean field technique, like the dynamical mean field theory, will give you a solution, which is actually this.
But this is at zero
current.
temperature.
Well, this is zero temperature. Yeah, this is zero temperature. And you may have different kind of current patterns, and this can carry or not momentum actually. That's in this case they do not carry momentum, magnetic momentum. So in this case, it's really not a ferromagnet. If you think at bilayers, in bilayers, when you have holes on one layer and electron on the other, if there is a superfluid flow of this exciton, then you will have a circulating current also there, because holes will have a current in the opposite direction with respect to electrons. Okay, so this is just to say that, okay, I have just 5 minutes and I'm closing. Just to say that at this stage, this is a completely open problem, I think, and the important question, the outstanding question here is how this thing will be actually in a real excitonic insulator material like TNS, for example, and now the presence of other type of ordering will affect this, the formation of this current pattern. So the last few minutes I want to show that even if you are not in a state with a homogeneous current, but you have just some current density around, which they sum up to 0, you can have actually the formation of a coherent state of light. And the way of seeing it, you can do this very simple problem in which you take a dipole and you polarize it, and you put it inside the cavity. So now I have a dipole which I described by a two-dimensional box. Basically, it's very simple. So you have this square well, this is a dipole. And I put this inside the cavity, and the important thing is that I keep all the spatial variation of the field, so I'm not doing any dipole approximation here. And then I put an external magnetic field in order to induce a current in the ground state of the system. So therefore, this is the ground state wave function of this dipole, and then it has this circulating current. Basically, it is a dimagnet. It will develop a magnetic moment of the opposite value with respect to the direction of the field. Now, what you do, you can put this current inside a cavity. Now, if you look at the light matter coupling here, there is a symmetry with respect to the center of the cavity, and this will basically be zero in this kind of odd cavity. So now what you can do, you can move your dipole from the center and then have non-zero interaction between the current and the field. This is just, if you now solve exactly this model, just by exact diagonalization of the photon and the matter, you see that as you move this dipole from the center of the cavity, you will create a macroscopic expectation value, well, not a macroscopic, sorry, an expectation value for the photon field, which basically means that you create some magnetic field inside the cavity. And this is just created by the fluctuation with the vacuum fluctuations. But also you can control and modify the magnetic moment. And in particular, in this case, this is negative. I don't see if probably the number are too small. In this case, you enhance the dimagnetic property of this dipole. You can also couple with a different mode now, which has a node inside here. And in this case, you will have basically you obtain the same, but instead that you will reduce the diamagnetic effect, because now the most important effect will be the magnetic field that will be created by the coupling with the vacuum fluctuations. So this is just to say that even in the case in which you have some current pattern, there is something very interesting to be investigated. For example, in the case in which you have not just a single dipole, but an ensemble of dipole, like the orbital ferromagnet that Andy was suggesting before. Okay, so this is just to end this journey into excitonic insulator and cavities. And in this talk, the important thing is that when it comes to the interaction with light, the excitonic insulator have very outstanding questions to be answered, I would say. And in particular, in relation to the formation of some polarized phase in these materials. And then it's a very interesting thing to investigate in real materials also in this space. And yeah, that's it. Thank you for your attention.
Chairman, I could start.
Yeah.
I let
Sure.
because just it goes to the last point, and then I give you the yes, because I think this is very interesting when you move the dipole in the unit cell, and then you get this induced magnetic. It's important because then what you have is already, if you have it there will be an additional force that acts on the dipole that will move it in a direction. Then you have a restoring force that the cavity will induce in the dipole that will create a dynamical motion that will tend to screen the current that you are generating. And this is something important because you can prove that this model that you are solving has a ground state.
This is the ground state.
No, but the ground state will be with one position in the cavity.
Sure. That's the
there is a restoring force that will act in the Maxwell field that also creates another.
Yeah, but for this one
I don't know.
one has to go to the multi-mode. So to investigate this in this single mode. Yeah.
No, I'm happy. Just Peter, sorry.
Yes. No. So actually, a couple of comments, maybe questions. So, by the way, thank you. Very nice. It's sort of a nice description. So, first question, I think, is, if you have all of these dipoles and you're coupling an orbital which is an S-like to a P-like orbital, I don't see how you will eventually avoid coupling to phonons, right? And actually, you will get, a Q equals 0 instability in a phonon mode, where the lattice will respond. So it's a nice theory of Tintelluride.
Yes.
Right. So then I think the other one, which I think is the same point that you're making, is that it would be much easier to think about this DC stuff classically. After all, if you just begin with Clausius-Massotti, You know, there's an instability which generates self-consistent dipoles if the polarizability is big enough. And then you actually have to think about the geometry because of the screening of all of these fields, right? And that I think goes back to this Volkov-Kopayev papers which are dealing with that. And the resolution of those instabilities, either in the longitudinal or transverse directions, I think are things which solve them by having boundaries with currents or boundaries with dipoles. But it is classical electromagnetic theory, I think, that needs to be done on top of this.
Well, yeah, this is.
So I'm not sure there are real mysteries there. I mean,
well, yeah, that's.
But by the way, if you could do something at the level of quantum fluctuations of single objects in the cavity, then I suspect there are things which are entirely new. But once it's condensed, it's sort of.
No, yeah, but that's exactly my point. Is that actually. Even without the cavity, I mean, this excitonic insulator state has some well interesting or weird properties, I would call it, in the sense that. So I agree with you that when you have the dipole, you will have the coupling with the lattice, and this is what at the beginning I was mentioning that in the real materials like TNS. Tomorrow we will have several talks discussing this.
By the way, sort of a last comment actually.
Yeah, sure.
In these models, biexcitons are stable, maybe weakly stable, but they can be quite stable. And that's a real boson, I mean, in the sense that helium is a real boson. It won't have a dipole, it won't have sort of channels to decay into, and it's the best place to get a kind of a real superfluid.
But I think that in the bilayer is
well, maybe by doing it with bilayers is one, or maybe just doing it by materials with very different masses for electrons and holes, so that you get the binding energy of the molecule to be much larger.
Thank you.
So yeah, I have a kind of the naive question about this phase of the polaritronic condensancy. So at the level of your model, you have basically some quadratic Hamiltonian for electrons, quadratic Hamiltonian for the holes, and some Coulomb between them. So from the point of view of the model, these are separate particles, electrons and holes. I can couple them to independent gauge fields and gauge away any phase. It just sounds really suspicious that the absolute value of the phase means anything physical. So are you saying that it matters actually? There are observables associated with like phase equals, I don't know, pi over 3 versus pi over 4 or something?
Well,
so yeah, if you condense it, you either get an electric or magnetic dipole.
Yeah. It's exactly in the single dipole is exactly this.
So, but at the level, if the model, your model does know about this. So the model chooses a particular phase, or
no? So the model, if you consider just the electronic model, it
can choose.
I mean, no, each phase you select, you will get the same energy basically. So the model is independent.
But they're totally different physical.
Yeah, exactly,
states.
exactly.
So
Once you couple with light, you will lower the energy of this state with respect to the other ones. That's yeah.
And then attack.
So you may have been trying to connect what you say on this slide to what you said at the end of the previous slide. I just wanted to make a comment on what you said on the previous
this
one before that, this one.
Yeah.
So you said here that if sigma x can never be non-zero, then you can never have an excitonic insulator. But I'm not sure that follows, because if I think of this kind of two-level system model, as written here, in the Coulomb gauge, then what I find is a ferroelectric transition of that model can occur, which leads to a non-zero expectation of sigma y, while it's sigma x that couples to the photon mode. And this corresponds physically to the distinction between a ferroelectric having a spontaneous longitudinal electric field and the superradiant state, if it exists, meaning a spontaneous transverse electric field, and the no-go theorem being all about transverse fields.
Yes, sir.
Yeah, and that's, yeah, I'm not saying that you cannot have a
No, no, I think
ferroelectric
this is-
transition.
yeah.
This is something, of course, in this model you don't have any type of interaction that will stimulate the ferroelectric transition. You will need some kind of, I don't know, some long range,
Yeah.
like Van der Waals interaction in this case. Yes, but in this case, yeah. What I wanted to say is that, yeah, I want to say that this is an excitonic insulator. It's a bright excitonic insulator. So
Okay.
that it has a finite dipole moment.
The transverse
Yeah.
excitonic insulator.
That's, yeah.
This is good.
So,
Okay.
so maybe a somewhat experimental question. So let's assume that indeed excitonic insulator exists in a 2D material, and that, I guess, what you're saying is that that would be due to coupling to all vacuum modes in the absence of a cavity. That's probably how one could understand this tantalum nickel selenide system. Is that a correct statement? Or so? Because
Well, yeah, it's a bit more complicated than this in the sense that, for example, in TNS, well, there is an excitonic mechanism at work. There is an electronic transition, which is of the excitonic type.
So you would not say that this is mediated by vacuum fluctuations?
No, I would not say this.
There's a comment on that.
Yeah, maybe I can just quickly. I hope tomorrow we'll have some focused discussions as to what is the correct symmetry breaking, what is the symmetry breaking at work in the specific case of TNS as compared to perhaps a broader class of excitonic insulator. I think there is a lot of confusion in that field. In TNS, the symmetry which is broken, in my opinion, is a discrete symmetry, and the transition is an Ising transition. And that's very different from breaking a U1 symmetry by condensing excitons, which is a much more exotic possibility, perhaps realized or realizable in bilayer systems, but you need an enlarged symmetry of the original model. So I hope we focus some discussions tomorrow on that, because that would help clarify the field.
Have all day to discuss that tomorrow.
Yeah.
Okay, the last question, if not, Dennis?
Oh, my question is just about this discrete symmetries, right? So if we have a discrete symmetry and we are talking about probably with some coupling with the lattice system will become ferroelectric, right? Why material TNS? It's not ferroelectric.
Yeah, well, that's
So what does it? Can you have a comment on this? Why on the theory point of view, what would expect? It's a ferroelectric, and which material it's actually?
well,
not?
that's. I'm not saying that TNS should be a ferroelectric or that every excitonic transition should be a ferroelectric. I'm talking only of excitonic transition between two bands, two levels, which have a finite dipole moment. And I don't think that this has been discussed in the case of TNS. I don't think that there is evidence of ferroelectricity. So it's, or you can also have a finite dipole moment between the bands, for example. Yeah, you can have also this. But let's say the local, since the excitonic order parameter is local, it can be that this P12, the local one, sum up to 0. This can be another possibility. So, of course, it depends. I would say that it depends on the microscopic property of your band system. For example, here there is an example of this matrix element for the simplest model of a solid, which is the chronic Penny model. Basically, you have just quantum wells. You have got just a periodic system of wells, and then you see that the sum of this is finite, which means that here you have.
I think this is a good moment to wrap up these 4 days of workshop on cavities.